Dr. Goetz, we can't hear you.
How about now? All right. Thank you so much, Annabelle. Or no, Harvey, whoever said it. Sorry, it sounded a lot like Anna. I wonder if I'm supposed to use, I don't care. It's not a discussion class, I just don't care. Okay, so like I was saying, differentials. They are important on their own, but really they're much more important as a stepping stone to integration, which is what we will be starting probably after winter break. That's usually kind of the way it works. Okay, so to talk about differentials, what we need to do is something that I told you not to do. That's it. We've talked about dy dx. And when we talk about dy dx, we usually think about it as a single thing. Okay? You as a class have not had this problem, but I've had other classes where they kind of wanted that to be an actual legitimate fraction and like move the dx places and stuff. And it turns out that you can actually do that. You can actually think of dx as some kind of independent variable and dy as some kind of dependent variable. And another way of writing this, of course, is f prime of x. So we kind of think about this as maybe we're going to find f prime of x using the equation of our function. But what I might really be interested in is if I make a small change in x, and dx is, as we'll learn when we do integration, dx is a really, 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 really small part of the x-axis, infinitesimally even. Okay. So what effect does making that very, very small change in dx have in dy? And we can use the derivative to help us figure that out. Okay. And so we can talk about things like, well, if the derivative, and what's the pre-calc way of talking about the derivative? The slope of the tangent line. Okay. So if you are at a part of the curve that maybe looks like this in here, then a small change in x is going to give me a very big change in y. Because my slope is so big, the slope of my tangent line is so big at that point. Maybe down here, a change in x isn't going to give me nearly as large a change in y. Okay? Because the slope isn't going to be as, slope of the tangent lines isn't going to be as big. And that is something called sensitivity. Okay. So this is really pretty straightforward. Do not overthink this. Okay, it has the potential for y'all to get all existential on me, and don't. Okay, so I think you have one example where we've got y is equal to x cubed minus 3x. Is that true? And we want to find dy at x equals 2, and if my little incremental change in dx, I'm sorry, is not 0.2, is 0.05. Okay, and everybody has that in their notes? Okay. So there's kind of two different ways that we can, or maybe even 3, that we can think about taking this derivative, okay? So one way is we can say that we're going to take dy dx. And what's dy dx going to be equal to? Minus 3, okay? And then if I consider my dx and my dy to be separate things, right, then I can say that dy is equal to 3x squared minus 3 times dx. I'm just going to move the dx to the other side. Okay. Another way to think about this is chain rule. Okay, and chain rule is important. It's one of those fundamental foundational things we need to understand. Okay, so if I think about it in terms of chain rule, I'm going to take the derivative of every variable separately. So the derivative of my dy, I'm sorry, the derivative of my y is going to be dy. Okay. What's the derivative of x cubed? 3x squared, but I have to take the derivative of the x, and that gives me a dx. Okay. What's the derivative of negative 3x? Negative 3dx. Negative 3dx. Okay. And those are equivalent formulas. Okay. One is just factored differently. So we know where we want to, what part of the curve we want to look at this change at, that's x equals 2. And we know how much we want to move away from x equals 2. And that's dx is equal to 0.05. So my dy, my change in y near x, when I take this very small change in x of 0.05, I can calculate what that's going to be. And I'm going to take the green equation just because it's fewer steps. So that's going to be 3 times x, which is 2 squared, minus 3 times dx, which is 0.05. So dy is going to give us, let's see, 2 squared is 4 times 3 is minus 3 is 9 times 0.05, and that should give me 0.45. Okay. I don't know what's going to happen, but I'd like to try this. What if we do it at a different x? Somebody pick a value for x that's away from 2. 12. What? 12. 12. Okay. So if we let x be equal to 12, we're going to take the same dx. I want to know what the same change in dx is going to give me. Okay. Then my dy is going to be 3 times 12 squared minus 3 times 0.05. We're going to need calculators for this because 12 squared is 144, but I don't know if I can do 144 times 3 in my head. That's 300, 420, 432. Minus the 3, but 144 times 3 is hard enough for me. So that's going to be 429 times 0.05, which I definitely cannot do in my head. So what do we got?
21.45.
21 point what?
0.45.
0.45. Okay. So we're getting a much bigger change at that value of x, okay, because of what the curve looks like. All right, questions? Questions, my Zoom friends? No? Okay. All right, so one of the things that differentials is useful for is looking at types of change or error. So we can kind of call that. And we can use linearization to help us figure out how much y changes if x changes by dx, as long as we stay close to what our value of x is. Because we know that a linearization is pretty accurate as long as we stay close to the point where we centered our linearization. Okay. So if we're going to let x equals a go to x equals a plus dx, or sometimes we say a plus delta x. So I'm just going to move a little bit, positive or negative. Dx can be positive or negative. Then if I'm talking about the actual function, I can say that y would then, delta y, which would be my change in y, or perhaps my dy, would be f of a plus dx minus f of x, right? I'm taking the difference between two positions, a and a plus dx. That's going to result in a change in y, f of a plus dx minus f of x. With me? This part isn't really calculus. Okay, it just looks calculus. But we know that sometimes using the function itself is very cumbersome. We can't do it. Okay, maybe it's a tangent, and I don't know what the tangent of pi plus 0.05 is. Okay, so if dx is small, we can use the linearization instead of f. So
How small does dx have to be? Like, is there like a fixed value where it's like?
no, it's just got to be really small. They're never going to give you like 12. It's going to be less than 1. You aren't going to have to judge whether or not dx is small enough. It's a good question. Okay, so that means that my f of a plus dx is going to be approximated by L of a plus dx. And remember that L of x is equal to f of a plus f prime of a times x minus a. Okay. And this is my x. That
That's what I understand. So the a plus dx is the thing that we have to find an easier way to like calculate.
Yeah, it's just that remember, we talked about it, sometimes the function is just like big and there's a lot of parts to it, and maybe I don't have my calculator. And the linearization lets me not have to use my calculator. It simplifies. So this is going to be f of a plus f prime of a times x, which is a plus dx minus a. So this gives us f of a plus dx goes as L of a plus dx, which is going to be equal to f of a plus f prime of a times dx. Right? Because my a's cancel. Okay. So really, my whole point here was that I wanted to figure out what delta y or dy is. So now I can substitute in for f of a plus dx using this. Okay. So that's going to be f of a plus f prime of a dx minus f of a or dy is f prime of a times dx, which is actually the formula we had at the beginning, but now we kind of understand what it is. Okay, we there? So this is kind of an actual change. This tells me how much y actually changes by. I mean, it might be an approximation, but it's telling me how many tick marks I have to count up my y-axis. Sometimes what I'm more interested in would be something called the relative error or relative change. And in that case, what I'm interested in is delta y or dy over y. And sometimes I think it's your book that talks about it as delta q over q, where q is just some quantity. And this is something that is actually kind of relevant right now if you're going to be a citizen scientist. Okay, like you can say, and I don't think this is true, but I'm going to make it up. Okay, that the state with the fastest growing COVID infections is Wyoming. It's not true, but let's just say it is. Okay, it's out there. And you know what? Wyoming had 15 new cases yesterday. Maybe I'm making that part up too, but I'm not off by much. Do you know how many new cases we had yesterday in Western New York alone? Not 1,000, definitely too many. It's like hundreds, not 1,000, but hundreds. Okay, so why is it worse in Wyoming than it is here? We have more people. Okay, so the increase for us, if we look at it per capita, and usually what we do is we look at it for 10,000 people or 100,000 people. Our increase is much smaller when you look at our whole population. So sometimes knowing what the absolute number isn't the best measure of what's really going on. Sometimes what you want to know is how is it compared to what the number actually is. If I'm hiking and, you know, and I need to go, I don't know, I'm trying to think, you know, like if I'm already up at 1,000 feet above sea level, it's another 5 feet. You know, if I'm down at sea level, 5 feet might mean a lot more. Okay, so it's relative, which is why it's called relative error or relative change. Sometimes another way to look at this is percentage error or change. And in that case, we're just going to take that relative error and multiply it by 100%. And this is over at 9:35. So we still have about 10 minutes. Okay, so I have, if I can get to them, a couple of examples of word problems that more have to do with like this percentage change and stuff. Okay. So, could somebody read the first one that has to do with the side of a square, please? Right, do you have those?
Yeah.
Thanks, Dagny.
About how accurately should you measure the side of the square to be sure of calculating the area within 2% of the truth?
Okay, so 2%, that's a hint, hint, clue, clue that we're talking about percentage change. Okay, so that means that I want to know that the change in the area over the area. And in this case, I'm going to take the absolute value of what that change is because I really don't care if it's bigger or smaller. And I'm going to multiply it by 100, but I need that to be less than 2%. And I want to know how accurate I have to measure a side. Okay. So I'm going to use my approximation to find delta A, which I can approximate as dA. Okay, maybe I need to cover a certain area so that something can happen. I have to cover it with water and make sure that I have enough water in my reservoir. So I need to make sure that my area is accurate. Okay. So what's my function A going to be if A is the area of my square? And let's say the side of my square, did they tell you that? No. Let's say the side of my square is S. Or side. How do I find the area? S squared. Okay. So if I take the derivative of both sides, what's dA going to be? 2s what? ds. Okay. So I've got, and this, like we said, is delta A. So what I'm going to do is substitute my delta A back into my original equation. Okay. And actually, I think what I'm going to do is I'm going to take that equation and I'm going to rewrite it a little bit so that I can say that delta A is equal to, I'm sorry, not equal to, less than or equal to 2 times A divided by 100. Okay, I just took everything that wasn't a delta A and moved it to the other side. Fair enough? Okay. So my delta A or my dA is 2s ds. But what am I going to let A be?
S squared.
Yeah, S squared. Good. And then I can cancel some stuff, right? So I can cancel my 2's. I can cancel one of my S's. And since my original error or my original uncertainty in A was a percent, then I probably want my uncertainty in S to be a percent too. Okay, so if I rearrange this a little bit, I could take ds over s times 100 is going to be less than or equal to 1. No, I don't, because my 2's cancel.
Oh.
Okay. And so my side, the measurement of my side needs to be accurate to within 1%. This is not a big part of the AP exam, but it is an application change. So let's not panic, okay? I see some eyes that are like, I have no idea how you did that, Dr. Goetz. No clue. Your eyes are all I can see. Let's try the other example. Okay, so somebody read us example 2.
Manufacturer contracts shipment coins to the federal government. The coins must weigh within 0.1% of their ideal weight, so the volume must be 0.1% of the ideal volume. Assuming the thickness of the coin does not change, what is the percentage change in volume of the coin that would result from a 0.1% increase in radius?
Okay, so what I'm trying to find here is the percent change in the volume. Right? That's what it says. What is the percent change in the volume that would result from a 0.1% increase in the radius? So that means that I can say somewhere that dr over r times 100 is equal to 0.1%. I'm just going to keep that over there somewhere. Okay. All right. So I'm going to need to know some things. What geometric shape is a coin? What? It's a 3D thing. It has a volume. So what's that thing? That's a circle that I move through space. A cylinder. What's the volume of a cylinder? No, that's a cone.
It is the pi r squared times h.
Yeah, pi r squared h. Okay. So it would be really nice if I could figure out what dv over v is, right? So I have this nice expression for v. Can I figure out what dv is? Now, they don't tell us, oh, they do. They tell us that the thickness doesn't change. And the thickness is h. Okay? So I can pretend that h is a constant, doesn't matter what it is. I'm just going to let it hang there. And then hopefully it'll cancel out. So what's the derivative of my volume going to be? What am I taking the derivative of? What variable? R. So what's the derivative of r squared? dr. 2r dr. So I've got my pi h, 2r dr, because I'm kind of using that chain rule thing. And now I'm going to take this information and substitute back into dV over V. So dV over V, dV is pi h 2r dr. Oops. V is pi r squared h. My pi h's cancel. One of my r's cancel. And I end up with 2 times dr over r. Dr over r is what I want, right? So this tells me that dr over r is 1/2 dV over V. Oh, that's not really what I wanted to do. I don't need, I mean, there's something wrong with that. It's just not helpful. I want to erase it. Okay, let's go back to this part of our equation. Okay, and multiply both sides by 100%. So dV over V times 100% is going to be 2 times dr over r times 100%. Right? I haven't done anything crazy. Whoops. What's this equal to? Dr over r times 100%. 0.1%. So that tells me that dV over V times 100%, which is the percent change, which is what I'm looking for, is 0.2%. All right, not magic, not rocket science, just unfamiliar. Okay, and again, not a really big part of the APCalc exam. Okay, but something that you should be thinking, you should know about. Okay. All right, so tomorrow we have class in the afternoon. I will entertain checkpoint questions from 4.2. We will look at 4.3, which you were supposed to read for today. I put up last night that 4.4 we're going to do tomorrow, Friday, right? And then the quiz is Monday. Is that true? Is there a quiz? I think the quiz is Monday. Okay. The quiz is 4.1 to 4.3 though, not 4.4. So please spray your desks. My Zoom friends, I will see you later or tomorrow. Okay, have a great day.
I did some Beetlejuice.